So quickly, the little review. Right now, the derivative, the big idea of calculus, is based on instantaneous rate of change. An instantaneous rate of change is the slope of a tangent line at a point. So if I wanted to find the slope right here at A, I would need to find the slope of that tangent line. But you only know the one point, the point that's on the graph. You don't know any other points. So what we do is we say, well, I could use point B, and that would find the slope of the secant line, but it would be a little bit off. But if I keep moving this point B closer and closer, and making this H smaller and smaller, eventually I would be right on there, the same as my tangent line. And so we write that, right? First of all, we say, well, the slope of the secant line is the rise divided by run, which is, in function notation, the y-coordinate of B would be f of x plus h, and the x-coordinate would be h. And if we figure out how much this difference is, it's just this y-coordinate minus this y-coordinate, f of x plus h minus f of x. And if this length was h, that would be your run, and that's your basically your formula for a slope. Now what we do with limits, and what Newton did, is he said, if we make h go to 0, then our secant line gets closer and closer and closer to our tangent line, and the limit will be exactly the slope of that tangent line. So we have now a formula for finding the slope at that one point instantaneous rate of change. Now what we can do with that formula, and what we did last class, is we figured out, and you can figure out the formula for the derivative of any equation. And we did this one, and did the limit as h went to 0, and we plugged in f of x plus h, which would be, that would be f of x plus h. Subtract f of x, which is divided by h. And what happens with this equation, and what happens every time with a limit, is nice things cancel out. You can already see that in the top, this 4 minus that 4 will go away. You can also probably see that you're going to have a 3x squared here. That's going to cancel out with that 3x squared. Eventually, what's going to happen is you are going to get once everything is simplified, you are going to get something on the top and something on the bottom, and what's on the top is going to have a common factor of h. What's nice about that is if I factor out that common factor of h, it will cancel with the h on the bottom. And the whole thing about this limit, the reason we couldn't figure it out is because if you plugged in 0 for h, you're dividing by 0, which is not allowed. But once the h cancels out, I can now plug in 0 for h. Right? You're allowed to do this. What is 6x plus 0? It's equal to 6x. And this, what we just found, is the derivative equation. And as far as understanding what's going on, okay, because this is calculus, if you understand what's going on, you're going to be set up. What did we start with? We started off with a parabola. That parabola was 3x squared plus 4. 1, 2, 3, 4. it would have a vertex at 0, 4. If you plugged in 1, you get 1, 7. You plug in -1, you get -1, 7. What the derivative does is it gives you a formula for the slope of every single tangent line that's possible on here. I can figure out at 1, 7, here's the tangent line. And I know that the slope of that tangent line, x is 1, 6 times 1 would be 6. I know the slope of that line is 6. I could plug in -1/2 and get something as a y-coordinate. And I could find the slope of this line to be -3, because I could plug in -1/2 for x into my derivative, and it will tell me the slope of that line is -3. And it's telling me at that moment, that's how fast the graph is changing. The graph is changing, it's going down 3 and over 1 per whatever unit of time you're looking at. It's giving you an instantaneous rate of change at that moment. So we do all of the definition of the derivative to find the equation, and now that equation can figure out every single slope of every single tangent at any single point on that parabola. That's the big idea. Why is that important? Well, how fast things are changing in an instant is really important to lots of applications in engineering, in business, in calculus, in mathematics. So we look at our next example. This is a graph that you could have graphed Can you see that that's an x cubed graph moved up 1? It would have a point at 1, 2. Right? If you plugged in 1, you would get 1, 2. You could draw a tangent at that point. How steep is it? What is its slope? This is what the derivative allows us to find. So right now, if we want to find out that slope, we would have to use Newton's quotient or the definition of the derivative and say the equation of the derivative will be the limit as h goes to 0 of our slope function, which is f of x plus h minus f of x over h. And we have to continue writing the limit as h goes to 0 until we can actually solve. I plugged in the easy parts. Can you see that f of x is really easy to plug in? Because we were given that f of x was x cubed plus 1. H is really easy to plug in because it hasn't changed. But what is f of x plus h? And I'm going to just do it off to the side here. Would you agree that that means we replace the x with x plus h in a function? So we would have x plus h cubed minus or plus 1. Now, the annoying thing here is you have to remember how to multiply x plus h times x plus h times x plus h. How do you multiply that out? Because that's what this means. F of x plus h equals x plus h times x plus h times x plus h plus 1. Do you remember how to multiply 3 things? Well, 2 things you could do. Method 1, you could multiply 2 of them, get x squared plus 2xh plus h squared, and then multiply that by x plus h and get it. Or maybe you remember how to use Pascal's triangle. This is binomial expansion. So Pascal's triangle, can you see with the exponent of 3 you would have 4 terms. So if you multiplied it out, you would get 1 x cubed plus 3, oops, that 3 was supposed to be blue, 3x squared h plus 3xh squared plus 1h cubed. So there I'm using Pascal's triangle and the binomial theorem to multiply it out. But I did that off to the side so that in this set of brackets, I can now replace it with x cubed plus 3x squared h plus 3xh squared plus h cubed. Hopefully you left enough space. I almost didn't. Now, once it's expanded, can you see, oh, I forgot something. That way you're going to come and change it nicely for me? Right? Because do you see that I didn't write the plus 1 there? And so there would also be a plus 1 there before we subtract. Good? Sorry about missing that plus 1. Do you see that some things cancel out? Can you see that this x cubed, when it's subtracted with that x cubed, will go away? And the 1, when it's subtracted with that 1, will go away. And what we're left with on top, every single term has an h. So we can factor it out. We would get the limit as h goes to 0. If I factor out an h, I'm left with 3x squared plus 3xh plus h squared. And on the bottom I have an h, and now this is what we've been waiting for. We wanted that h to cancel out and go away. And now you can apply the limit. So what's our derivative going to equal? Well, if I plug in 0 now, the second and the third term would go away, and I would just get 3x squared. So now my original question was, how steep is that line at 1? The slope of this line would be equal to 3. Because I could plug in 1, the x value. I now know the slope of that tangent is equal to 3. What about at 0? What's the slope of the tangent there? Plug in 0. That one would be completely flat. Our tangent would be 0. Can you see at -1? We'd have the point -1 comma 0. If I plug in -1, I'd also get a slope of 3. And so if we use the definition, expand things completely, factor out the h so that it goes away, we can do the limit. And then we can find the equation of the derivative. How long did this question take us? About. Without, if we subtract the interruption. 4 minutes? 5 minutes? Was it about? 4 minutes. Okay. The beautiful thing about calculus is we are going to learn strategies to shave off. If this took us 4 minutes, we will learn strategies to shave off 3 minutes and 58 seconds. That is crazy. Can you imagine? That's like, can you imagine if they invented something that would shave off, that percentage of your schooling? So instead of spending 12 years in school, they're like, we figured something out. You can go for 15 minutes now and you'll be done. 15 minutes. You're like, okay. Well, at minute 10, I decided I was going to drop the IB program. Or you have to decide to drop the IB program at minute 12, right? From 12 minutes, in the next 3 seconds, you wrote 5 IAs. Okay, that's good. That would be amazing if you could shave off that much. We are going to do that today. But first of all, we are going to do the long method one more time. Okay? I'm going to tell you that in the short method, you're going to look at this, you're done. That's how fast it's going to take to find the derivative equation. But right now, what do we have? We've got a function. Can you see that it's a parabola? Can you see that you could, probably graphing that parabola would be fastest using the x-intercepts. You could factor out an x to tell that there would be one x-intercept at 0 and the other x-intercept at 2/5. You could tell that that parabola opens up like this. This is the parabola that we have. What is? Okay, we have that nice x-intercept. Question is, what is the slope of the tangent line at 2/5? Well, I would need to have my derivative equation to figure that out. How do I find my derivative equation? I'm going to have to do the limit as h goes to 0. Here would be f of x. This is easy. Here would be h, right? This is f of x. This is f of x plus h. I did not, most likely did not leave enough room. I'll make my bracket a little bit bigger to make it all fit in. You would have 5 x plus h squared. Would you agree that x plus h squared would be x squared plus 2xh plus h squared? Minus 2 times x plus h would be minus 2x minus 2h. Because you distribute the minus 2. I'm going to take an extra time just to distribute the 5. So can you see that I would have 5x squared plus 10xh plus 5h squared minus 2x minus 2h once that is all multiplied out. So what's the frustration with this method is just the x plus h part takes some time to simplify. But if you plug it in, nice things start to happen. Can you see that when you subtract, this 5x squared will cancel out with that 5x squared. This minus 2x would cancel out with that minus 2x. And can you see that everything that's left in the top has an h? So we can factor that h out. Again, write the limit as h goes to 0. Factor out the h, I'd be left with 10x plus 5h minus 2 all over h. And now my h's cancel out. And that's what was causing the problem in this limit, because it was causing us to divide by 0. Now you can plug in h equals 0 and figure out the equation. That our derivative is going to equal 10x minus 2. How's your mental math skills feeling today? Can you tell me that slope? Plug in 2/5? No? 2. Right? Because I plug in 2/5, I get 20 over 5, which is 4. 4 minus 2. Good? So we know that the slope of that line is 2 at that moment. And again, I'm going to tell you that we are about to be able to just look at the original equation and go, I know what the derivative is. Were any of you cheating? Have you looked this up already? No? No cheaters in class? Like, it's kind of exciting that we are going to be, like, you haven't probably done this in math since grade 9. In grade 9, you had questions that you could look at and just write the answer. You had questions like, x plus 3 equals 7. Right? You'd be like, and your homework would be like, teachers would be like, we have to give you like 50 questions, and you're going to be done in 7 minutes. And you haven't had that for a while, but we're going to get that again in calculus, where it's going to ask you, what's the derivative of this question? You're going to be able to just look at it and say, 10x minus 2. Right? You're going to be able to look at this one and just say, oh, it's 3x squared. So there's a pattern there that's going to help us figure out. But now we're going to do one more tricky one with a square root. Find dy dx. dy dx is just another form of the derivative. The limit as h goes to 0. I'm going to tell you that this is a harder derivative. If the last derivative took you 2 seconds, this one's going to take you about 4 seconds with the shortcut, so it's harder. But with the definition, this is going to be 3x plus h minus 3 root x over h. And there's not much you can simplify here. So we're going to have to, in our memory of math done in the past, there was a place in mathematics where you had to get rid of square roots. Do you remember in grade 11 when you weren't allowed to have square roots in the denominator? And you had to, in English we said, rationalize the denominator. Get rid of the square roots. So you would have questions like this, and they would say, that's not simplified because you have a square root on the bottom. And these ones were easy, because all you had to do to get rid of the square root is multiply the bottom by root 3, and then you'd have to multiply the top by root 3, and you would get 5 root 3 over 3. And you got rid of the square root. Do you remember getting rid of the square root? When you had that on the bottom? What did you have to multiply by? And why? If you remember why, you'll remember what you had to multiply by. But most of you don't remember why. Root 3 plus 2. Why do we multiply by root 3 plus 2? What does that make the bottom? Yeah, difference of squares. Like, and check it out. If you have a difference of squares, right? Like, for example, something really nice like x squared minus 9 is x plus 3, x minus 3. But what makes it a difference of squares is this is something perfectly squared, x times x, and 9 is 3 times 3. And so if I make a difference of squares, I get to square the first number, and I get to square the second number, and put a minus sign in between. Can you see that that gets rid of all your square roots? Right? So in this, that's a connection between where you've done something like this in the past. In this question, we are going to do the same thing, but instead of getting rid of square roots on the bottom, we want to get rid of the square roots on the top. And so I'm going to say, okay, on the top, I can multiply by 3x x plus h plus 3 root x, and 3 root x plus h plus 3 root x on the bottom. That will make the top this one times this one. Can you see that 3 times 3, that would be 9. And root x plus h times root x plus h would just be x plus h. Minus this one times this one. Well, 3 times 3 is 9. And root x times root x is just x. Over. And on the bottom, I'm not going to multiply it out because I like it factored. I want to cancel out that h. So by multiplying to get rid of the square roots, can you see what the top is going to simplify to? See that it's just going to become 9h, the 9x and the 9x are going to cancel out. How nice is that? That I'll just have limit as h goes to 0. The top will just be 9h. I've already got the h all by itself on the bottom. And my h's will cancel. And that was the h that was causing us problems to divide by 0. And so now I can apply h equals 0. Can you see if you plug in h equals 0 now, you're not dividing by 0 anywhere. Can you see on the bottom you would have 3 root x plus 3 root x? That's going to be, on the top is still going to be 9. But 3 root x plus 3 root x would be 6 root x's, which would be the same as 3 over 2 root x's, which is the same as 3 over 2 x to the half, because you can change square roots to exponents. And when we do this as a shortcut, which will take us 4 seconds, because it's a longer one than the 2-second questions. When we do this as a 4-second question, our answer will actually show up like this. Do you remember your negative exponent rule moves an exponent to the other side of the fraction? So somehow we're going to be able to start with this, 4 seconds later get to this without having to do all the stuff in the middle. Does that mean you can forget how to do all the stuff in the middle? No. You're still expected to know how to do all the stuff in the middle. Sometimes university calculus classes spend like 2 weeks before they show you the shortcut. And they see kids going, how am I ever going to do this? And you've already learned the shortcut and you're like giggling to yourself, like, oh, I figured it out. Okay, so, okay, part B to this one. If you want to find the gradient, that's another word for slope, of the tangent line when x is equal to 4. Well, we figured out that the derivative was 3 over 2 root x. Actually, in this question, they used this notation, right? They said find dy dx, so we should keep the same notation that the question asked for. We found the derivative to be this. Is it hard to plug in 4? At x equals 4, the slope of the tangent would be 3/4. I just plugged in 4, square root of 4 is 2, on the bottom 2 times 2 is 4, and that would be the value. Now your calculator has some nice built-in functions, so if you take out your calculator, In fact, we can do the question that we just did and see if we're right. Did you buy those at Costco? Steal them from work. Nice. 2 days ago, they gave them out as samples. We can talk about Costco a little bit more if we'd like while we're waiting for the calculator. So while you're waiting, find it, math button, go to number 8. You'll get the derivative. The function you can put in 3 square root of x. You have to put x in again, and then we want to find it when x is equal to 4. So, math button, number 8. If you have the newer version, it comes up like this. So you have to put d dx of 3 square root of x, because that was our function, when x was equal to 4. We figured out to be 3/4. This should be the same thing. Ooh. Has a little bit of error. We're smarter at this moment. This is fun. In calculus, when you're smarter than your calculator did thousands of calculations to come up with 0.750000000006, and then said, I'm too tired to keep going. This is good enough. And we've used calculus and figured it out to be 0.75 exactly. And we are at this moment smarter than our calculator, because it has some error. Did anybody have a different error than my error, depending on how fast your calculator is or how slow it is? Sometimes it gets different errors. Sometimes it comes out perfect. Did yours come out perfect? So maybe its operating system is nicer than the Texas Instruments. So it finds the slope at a certain point, and we could do different questions. You could try these ones. How useful is this? Well, you can check things, but for the most part, you have to show your work with derivatives. So we actually don't use this button very often. But you could have very crazy functions, like this one here. The instantaneous rate of change of the natural log of sine of a parabola at pi over 4. This is a little crazy. Okay, so I'm going to end this video here.